I don't know if you've noticed, but some people seem to be completely unable to do things like everyone else. I'm afraid that at Le Chemin de Traverse, most people fall into this category. For instance, to come here all the way from Switzerland, do you think we came by train or by plane? Not at all. We came by e-bike. But wait, when I'm saying e-bike, you probably picture something like that. That could have been accurate if we were reasonably sane people. But bikes, in this case, were one-of-a-kind vehicles, a dual-motor semi-recumbent tandem, and a solar velomobile. Anyway, if I'm here today, it's probably because Le Chemin de Traverse are an IT company of some sort, right? Wrong. We are a collective of musicians and artists that usually travel off the beaten track. For instance, if one of us tells you she plays the flute, don't take it for granted you know what she does. But as fascinating as it is, the contrabass flute is not the focus of today's talk. I'd like you to meet the harpeggi, which is also played at Le Chemin de Traverse. The harpeggi is an instrument built like a combined electric guitar and bass, but played like a keyboard. It was invented less than 20 years ago, and playing it is still very much an exploration into unknown territory. Oh, sorry. Okay, thank you. I actually considered taking a harpeggi with me to demonstrate the thing, but I must say that on an e-bike it wasn't very practical, so I decided to come with videos instead. In this example, the sound of the harpeggi is rather acoustic, but as you might know, playing an electric guitar or a harpeggi through a flat amplifier is likely to sound pretty bad. So even the simple example you just heard, the harpeggi sound is processed in various ways before reaching your ears. Of course, to process the sound, we could use commercial and analog pedals or dedicated sound software on a laptop. But did I mention we have a tendency to do things differently? So we decided to develop our own software to process the sound of our instruments. As we believe in free and open source software, we decided to use only that, including for the OS. As for the language, natural choices would have been C or C++, or maybe Go or Rust. So we thought, why not use Python? So here is what I'm going to talk about. How to code real-time audio processing chains in Python, how to make it work on a headless computer, and what are the possibilities to interact on stage with a headless system. So first, real-time FX programming with Python. Is this even possible? As it happens, there's a wonderful module called Pio that allows to do exactly that. Pio is developed by Olivier Bélanger in Montreal. It includes a very efficient sound engine written in C that runs in its own thread with high OS priority. It allows to include signal processing chains directly in Python scripts and to manipulate them in real time through the interpreter. As such, it combines very nicely the efficiency of a C implementation with the versatility of Python. Pio was first developed for sound synthesis and algorithmic composition. Here is an excerpt of a piece written by the original author of Pio, Olivier Bélanger. So that's an example of Pio used for sound generation. But Pio is also an awesome tool for real-time audio processing. As an example, let's see how we would set up a simple script to get audio through without any additional processing. First, import Pio, of course. Then create the audio server. Then create your patch itself. Here we create a simple input object that will go directly to the audio output. Then start the server. So this will launch a thread with high priority. And most importantly, many beginners forget that, keep the Python process alive. That can be with an input like here, and you just have to press enter to keep the script, or an infinite loop, or a GUI main loop, or anything really, but you have to keep the process alive. If you don't do it, the script will exit immediately, stopping all audio processing, obviously. Anyway, what's important to understand there is that Pio object represents streams of audio data that you just connect in diverse ways, but the processing itself is managed by the audio server. So, in principle, this code is all you need to get low latency audio through. In practice, you'll also need a properly configured OS, but more on this later. Actually, a arpeggio has two outputs, one for the bass strings and one for the melody strings. Taking this into account in Pio is just a matter of creating two input objects and mixing them into a single stream. Fancy some reverb? Just feed your mix object into a free verb object with appropriate parameters like the size of the room or the level of high frequency attenuation. And it's already sounding much nicer. But we can do much more than using predefined effects. You know the effect called auto-wah? It sounds like this. Okay, the idea is to boost a portion of the audio spectrum, like with a bandpass filter, sorry. And the center frequency of this filter will depend on the loudness of the sound, okay? So it's pretty easy to understand. To do this with Pio, first you can create a follower object that will create a stream that represents the mean amplitude of the signal, so basically the loudness of the signal, varying in time. And then you feed that into a seek2 object that will do some portamento on the values, so that will smooth out the irregularities of the signal. And then you feed the sound of your instrument into a bandpass filter, so a B-quadratic filter of some sort, with the center frequency equal to the smooth out amplitude we created before. And there you are, a nice custom auto-wah for your arpeggio. Now that you know how it works, I will play it once again and try to see and listen if you can relate the code to what you're hearing. Okay, I see some people nodding, so I don't know about you, but I think it's pretty cool to have only a handful of lines of code and have something non-trivial like that, which is really working. It's usable in a gig. But as cool as it sounds, you probably don't want to always play with the effect activated, right? So using a selector object allows to output the dry signal when the voice parameter is set to 0, and playing the sound with the effect when the voice is set to 1. And you can also set voice to any value in between, and it will interpolate and get a mix between the two. So that's it, or almost. Maybe just a little practice with your instrument, and you're ready to gig. Just pack a laptop, sound interface, cables, and everything. And oh, don't forget to open the terminal and manually launch your script before you're playing. But wait, couldn't we get a step further and have a self-contained, headless, ultra-portable unit that would be much more convenient? So let's have a try at a headless setup. Don't try this at home with your computer, it might turn bad. First, we'll have to see what kind of hardware we need. Actually, if you ask any musician working semi-seriously with real-time audio what computer they are using, they will almost always mention a brand named after fruit. So we thought, what if, for once, we followed what others say? And that's why we did select a brand named after fruit. Think different, they say, I think. Having decided this, we went through a very systematic model selection process. Namely, we had 2 Raspberry Pis lying around. One was an ancient Model A from the time of dinosaurs, and the other one was a Raspberry Pi 3 Model B that ran one of the best single-board computers in 2016. But the question is, can we achieve high-quality, low-latency audio processing on a 2016 single-board computer? Of course, to get high-quality sound, you cannot use the built-in mini jack sound interface of the Raspberry Pi. So the first idea was to get a compact USB-powered sound interface. It did kind of work, but we encountered some problems, namely 2 problems. We had a high-pitched hiss, like really high and very disturbing, that was due to electric noise caused by the switch mode power supply of the Pi. And in certain situations, we also had a low buzz sounding very much like a ground loop, except that no ground loop was possible as the Pi power supply is not grounded. It was quite strange because it would disappear. I didn't notice it at once because if I had a monitor plugged into the Raspberry Pi, which I would have in development, it would work. And as soon as I would unplug the monitor, the buzz would appear. Actually, after some digging around, we determined it was due to a floating ground, not a ground loop, but a floating ground, as the amp we were using is not grounding the signal. We could have solved both problems easily by using a sound interface with, which is powered from a wall socket. But that would have defeated the goal of getting a simple self-contained unit. So we had a look around, and that's why we got interested in the Pi sound, which is a Raspberry Pi hat with high-quality stereo audio in and out, MIDI, and a button. You'll see that the button is very convenient. Even better, you can order a 3D printed case that makes the combo perfectly usable on the field. We hoped that the Pi sound would have some kind of filtering that would remove the high-pitched hiss. And actually, it does, so that was one problem less. But we still had the floating ground buzz. I will show you how we solved it, but please don't try this at home unless you know exactly what you are doing. We removed the phase and neutral pins from a normal Swiss plug, a Swiss power plug, to keep only the ground pin. And then we soldered this ground pin to the ground thread of a USB cable. Okay? And now you just have to plug one end of the connector into the wall socket and one end into the Raspberry Pi. And voila. The Pi is properly grounded, and the buzz is gone. It does look almost as strange as some of XKCD's cursed connectors. And you could easily destroy your hardware, maybe home or even body, if you do it wrong. But if you do it right, it works. Note that many amps ground the signal, or if you go through a mixing desk, many mixing desks also ground the signal, so you don't have this problem. But if you happen to plug directly into an amp that doesn't have the possibility to ground the signal, you'll have to do something like that. But if you try it, don't tell anyone that you got it from me. Okay, now that we have working hardware, let's see what software we are going to use. Regarding the OS, the main requirement is that we want a setup that allows for a round-trip latency under 10 milliseconds. Anything more than that makes it very awkward to use the device for many musicians. Linux is notably efficient for this kind of thing, so that shouldn't be a problem even on older hardware. But Linux is also notably difficult to set up for reliable, very low latencies. So we might have to struggle a little bit there. Just a quick note for people who already played with low latency audio on Linux. Raise your hand who already tried Jack and this kind of thing. Okay, some people. If you're using a GUI front-end to the Jack audio daemon, it's likely to display a latency value like 4 milliseconds, 8 milliseconds. That's the inner latency of Jack, but that isn't the round-trip latency, which includes the converters, DAC and other way, and everything. And so the round-trip latency will be much higher than this value indicated by Jack. But the round-trip latency can be measured with extreme precision with the Jack I/O delay utility and hardware loopback cable. So that's something people don't usually do, but just plug a cable in the out of your sound interface and back in and then launch Jack I/O delay, and you will have really hard numbers about your latency. So back to OS selection. First, we tried the most obvious Raspberry Pi OS, but we couldn't get it to work with low latencies, partly due to the lack of a real-time kernel. Admittedly, we could have patched the kernel sources ourselves and cross-compiled them, but, Anyway, we then tried Debian, which does include a real-time kernel in its repositories. It does need quite some tweaking, but it's absolutely possible to get it working. I have a blog post about it if you want to see all the tweaking that's necessary, but it's possible. But there's a much easier way. Blocas, who also make the Python head, provides a distribution especially tailored for low latency audio on the Raspberry Pi. So just flash it on an SD card and everything works out of the box. So it's like you need 3 days to find the right distribution, and then it works in 5 minutes. The next step is getting our FX script to launch automatically when booting the computer. You don't want to plug in a keyboard in the screen just to launch the script, right? The right thing to do here seems to be writing a systemd unit. There are quite some concepts involved here, but the most important things are provide the command to launch the script, include some magic incantation to allow your script to run with real-time priority. That's also like 2 days to find this, or 30 seconds to copy and paste this. So, and place this file in the right systemd folder. Now, enable your systemd unit, and it will start automatically on boot. So you just have to boot your computer, and you have sound. Everything is working nicely. Now, if all you need is a fixed effect from the beginning to the end of your gig, you're done. But chances are that you will want to activate and deactivate effects and fine-tune parameters. For this, you have mainly 3 possibilities: using MIDI, OSC, or the Python button. Of course, it's also possible to combine these technologies in any way you like. So, first, let's see MIDI. Pio has first-class MIDI support. So if you've got a MIDI controller of any sort, it's very easy to use it to control your script. For example, suppose you want to use a MIDI expression pedal. A MIDI expression pedal is something you have under your foot, and you can just rotate it like that, and it's like a 0 and a maximum, like that. Very simple device. So you want to use this to control the volume of your instrument. So you can do like a fade out or play softer and then louder or something like that. So first, you have to create a MIDI CTL, so MIDI control object with the relevant channel and control number parameters. That depends on what your MIDI device is sending. Then, like before, you have to smooth out this signal to avoid clicks when the value is jumping around too quickly, or you will have discontinuities in your signal. And then you use this trim to control the multiplication attribute of the object whose volume should be controlled. That's it. Your pedal now controls the volume of your instrument. So, very easy. Now, let's try something fancier. For instance, let's implement an infinite sustain pedal, still controlled by an expression pedal. The idea is that when you raise the pedal, it should record a short portion of audio and then loop it with a volume controlled by the pedal position, and loop it until you get the pedal back to 0. Okay? So you can just freeze the sound you're having right now and play with it louder, softer, and then cut it. There are some commercial pedals doing this kind of thing. They are at least, I'd say, twice as expensive as a Raspberry Pi and the hat. So if we get to it, it's not a bad result. To make it even cooler, we're going to make it double buffered so that you can have the loop fade out while you are recording the next loop, and you have a small overlap so you don't have a hole between your sounds. Now, to implement this, you'll need a buffer to store the audio data, a so-called table rec object to record audio into this buffer, and a looper object that reads from this buffer and plays several simultaneous instances of the sound with crossfade to avoid clicks at the beginning of the loop. You know, if you play a loop just like that, row, at the place where the end goes to the beginning, you will have a discontinuity in your signal and you have a click. But if you play two instances of the sound, not at the same time, and you just fade in, fade out the beginning and the end, you get a loop like that. And here, the crossfade has many parameters. That means that we will have different values of length of crossfade simultaneously playing. Okay. Then we'll have to write another class that will contain two of these sustainers. Remember, we wanted it to be double buffered. And that's interesting, two threshold objects. In Pio, threshold object is an object that will detect when a given signal crosses a threshold, either going up or going down. Okay? And its output will be 0 all the time, except at the exact moment when the signal crosses the threshold. And then you feed the threshold objects into those trig func objects that trigger a function, obviously. So when the threshold fires, it will call a Python function. And in this Python function, I don't have the code here, but it will simply you know, run the table rec that will record audio into the buffer and begin to play the loop. So there is a little bit more code than what I'm showing to you, but the whole implementation is 45 lines of code, so it's still very manageable. And here is what it sounds like in a setting with no dry sound, so only the effect, to try and emulate the sound of an organ. Okay, if you're looking carefully, you might have noticed that the sound comes quite a while after I hit the strings. Of course, it's not latency. Latency is under 10 milliseconds, so you wouldn't notice it on the video. It's just that I hit the strings and I let the sound stabilize before recording it, because a defining characteristics of the organ sound is an almost complete lack of attack. So I hit the strings, and then I record to play the loop. And the timing is a little bit difficult to find, because if you activate the effect too early, you will get the attack of the sound. And if you do it too late, it will be very soft. So you have to practice a little bit to find the right timing. But the reward is a completely unexpected sound from the arpeggio, which I like. Did I mention we like to do things differently? I don't remember. Anyway, that's it for MIDI. As you see, it's quite easy to use MIDI in this setting. Another possibility for user interaction is to use open sound control. Maybe you're not all familiar with OSC. It's a UDP-based network protocol that was designed to be the successor of MIDI. Pio also supports OSC natively. So, for instance, if you want to control the auto-wah we've seen before with OSC messages, all you have to do is create an OSC receives object specifying the port and addresses it will listen to. This object will behave like a dictionary that maps addresses to streams of data. So just replace the fixed values we had in the code before with these streams, and you can control these values with OSC message, like sending /war, an integer value 1, I want to activate the war. Now, of course, sending messages from the terminal is not what you want to do on stage. There are several programs that let you design user interfaces that send OSC messages. But if you want to stick to open source, the easiest way is to use open stage control. I won't go into details today, but it lets you design complex UIs that send and receive OSC messages with several synchronized clients and many nice features. So have a look if you're interested. This is definitely a good way of using OSC to build a traditional user interface. But you can also get more creative. In this video, the dancer has two inertial measurement units on his wrists that allow him to control the effects of the arpeggio with his motions. As a side note, it's very interesting to play through an effect that you don't control yourself, because you are playing and you don't know exactly what will come out of your instrument, and that's a very interesting experience. Well, OSC, as you see, is a very versatile protocol, and you can do all kinds of crazy things with it. But both MIDI and OSC require an external device to interact with your Raspberry Pi. But if you are using the PySound interface, you can also use the PySound button to interact with your computer with no additional hardware, which can be convenient in some cases. Actually, the PySound has only one button, but you can assign scripts to many actions like button up, button down, single click, multiple clicks, I think up to 8. And also long presses like press during 1 second or 3 or 5 or 7. Of course, the 7-second long press is not very usable in a live gig, like, I press the button and wait for 7 seconds, just smiling at the audience. Oh, yeah, I have my effect now. But suppose you want to activate your auto-wah effect by single-clicking the button. That's quick and convenient, so that does make sense to use it like that. For that, just write a script, a bash script, that sends the appropriate OSC message when called, and put that script in the right directory, and use the PySound config utility to link it to the right action. So quick and easy. And note that Patchbox OS also comes with some default useful actions, like shut down on a 5 seconds action click. If you've had a try on a headless setup with a Raspberry Pi alone, you've certainly encountered the problem, well, how do I shut down this thing properly now? So that's problem solved. So that's a good way to do things. Now, as a little goodie, some debug information. When you're writing your code, you might encounter a situation where you hear artifacts in the sound, but you are not sure whether it's a bug in your code or just the Raspberry Pi that is not keeping up with what you are asking. That's why we included in our UI debug information about the DS payload and dropouts, also known as X-runs in the Jack jargon. If you worked with Jack, you encountered this word. So DS payload is not exactly the same as CPU load, but it's an information about the ability of the computer to keep up with DSP processing. And dropouts happen when the CPU cannot keep up and some audio samples get lost. This usually results in ugly clicks in the audio when it's not too serious, or the audio completely distorted if it's really serious. Pio doesn't cover this kind of thing, but of course, the Python ecosystem has everything it takes to monitor these things easily. So there's a Jack client package that allows to monitor the Jack daemon status, and Python OSC provides an easy way to get OSC messaging. So you can register code that will execute each time an X-run occurs. And there you can count the number of dropouts and the time since the last one, which is useful information. And now periodically send the relevant information to your open stage control UI through OSC, and you will know what's actually happening on your computer. So, to a quick conclusion, I think the main takeaway of this talk, if you want to try it yourself at home, except for the plug thing, remember. So the main takeaways are that even on older Raspberry Pi, it's perfectly possible to do low latency audio processing. And it's even fun to do it with Python Pio, sorry. Also, the Python audio interface and Patchbox OS together make things very easy. And probably you should use the systemd for auto-starting thing. And interaction through MIDI or OSC is quite easy to do with Pio. But most importantly, always remember that music is the goal. So your audience should not be listening to an instrument played through a Raspberry Pi programmed in Python. They should simply be listening to music, right? That's why I will finish my talk with some more music. Maybe it's not a common way to do things in a tech conference, but did I mention we have a tendency to do things differently? Thank you.
Thank you so much. That was amazing. Do we have any questions from the audience? Yeah, you can line up at the mic over there, or I can just pass mine if you're like somewhere in front. Yeah.
Hello. So this is really awesome. And I just wanted to ask, have you looked into Pipewire as using it instead of Jack?
Into, sorry?
Pipewire for...
yeah, actually, I'm using Pipewire on this computer, for instance. I have a tendency on the computers I use for gigging to be very conservative. So I have a setup that works with Jack, and I have a tendency to keep it. But probably at some time I will switch to Pipewire. Yeah, you know, around Jack there are many, like I said, like utilities for measuring latency and things like that. And I know the ecosystem, and then I'm a little bit reluctant to switch. But that's definitely a long-term goal or mid-term goal to switch to Pipewire.
Yes, very nice. Thank you. I was thinking, did you look into pushing your Pio project to a microprocessor and flash it and have a guitar effects box that runs on a microprocessor?
No, actually not. That's not a thing I'm familiar with. So that could be very, very interesting, but I'm not sure whether it's possible. I had a try with middle solution, which is using the Bella. I don't know if you know the Bella board. It's a board that runs Linux, but with a CPU core dedicated to audio processing outside of the system scheduler, and you can get insanely low latencies with this. But it was quite difficult to get Pio support for this setting, and the gain was not that much. But I didn't go to this. Maybe we can. If you've got an idea about how to do this, we can talk about it later, because
yes.
I'd be interested.
Yes, thank you.
Thank you.
Really interesting project, and really interesting to see how you got it to work in real time with digital signal processing. Regarding controls, did you try to use the GPIO pins of the Raspberry Pis to attach more pedals and stuff?
No. Actually, I've been doing this kind of processing on a laptop for quite 15 years now. And so I've got like MIDI controllers and everything it takes, and it's easier and quicker for me to reuse that. So there's certainly something to do with this, but actually, I think most of the time it could be more convenient to use OSC with a remote device, like a cellular phone. You have an EMU in there, so you could control something that just like that, and you don't have like a cable attached. So I feel I will probably go in this direction instead. But yeah.
Thank you.
Okay, thank you so much. Any more questions from the audience? None. Okay, thank you once more time.
Thank you.